actually coming across. There was the additive synthesis thing in the homework, and there was some trouble with the phases. I haven't checked the labs yet. And like I told you, if you just passed in the phases, I'm happy with that. That's okay. But if you want to do the complex amplitude method, we are now going to talk about how to go about that. I had a copy of this open that was going to be useful. Okay. So we can set up a frequency vector, say f equals 200. We'll call that hertz times harmonics. So f is going to look like this. We're generating frequencies 200, 600, 1000, 1400, and 1800. And then we're going to make amplitudes of 1 over 1, 3, 5, 7, 9. So those who finished the lab, what signal are we gearing up to make here?
Sawtooth. Was that the answer for the lab from last time?
One of them was a sawtooth, this one's not.
Oh, sorry.
This is a square. And you can recognize the square as all of the odd harmonics, 1, 3, 5, 7, 9, generating these frequencies, and amplitudes that fall off as 1 over the harmonic number. And what those look like in decimal is this. Are we happy so far? I like to see heads. I like feedback. Awesome. Now we're going to do this. What are we making right now?
Your bins.
Yep. So this is our sample count, right?
Yep, those are your bins.
Well, if we take it to the frequency domain, you're going to have that many bins. Right now, this is just a count of our samples. Mm-hmm. Excellent. So we can do y equals a times the exponential of j times 2 pi times f times n. And this is the form the math is going to take. We're going to flip f in order to do the matrix multiplication. The matrix multiplication is not something you have to worry about. There is the question in the homework that asks if you can do it in one line versus using a loop. This is how you would do it. The reason this works is because you have f prime, which is 5 by 1, n, which is 1 by 3000. So 5 by 1 times n by 3000, for those who have taken linear algebra, is going to give you a 5 by 3000 matrix. This is 5 by 500. Why does it do that? Did I do a dumb thing? There we go, 5 by 3000. And then this is going to take the exponential, complex exponential of it, so it's going to act element-wise on those. And then we have the a, which is a 1 by 5. A 1 by 5 times a 5 by 3000 is going to get you down to a 1 by 3000. So it may not be obvious, and if you don't understand, that's okay. This is linear algebra, not signal processing right here. This will do the additive synthesis in one line. It's not important that you know the linear algebra. That's just for those who are curious. And then we're going to plot it. And we're going to plot the imaginary component here. The reason we're plotting imaginary and not real is because that's what makes the phases work out to get the sinusoid. So what happened here? Sample rate. We're looking at just noise right now. And the reason is because we forgot to include a sample rate. So to look at this again, we're going to see this guy here, which is cool. It looks like a square wave to some degree. We can make it look more like a square wave
Why are you plotting only the imaginary part?
Because, well, I could plot the imaginary or the real part. In this case, the imaginary part is what it takes to get the phases right, so it looks like a square. Either way, it's going to sound like a square. This is the problem that you and Iran were playing around with, actually.
How will the phase change what it looks like?
Excellent question. That's exactly where I was going with this next. So if we take this and add a phase component, let's say we're just tossing some random phase on there.
Before you do that,
Russ.
can you just plot the real part, just for fun?
Absolutely.
Wait,
Oh, that is.
Yeah, that's what I got.
wait, you still have that other,
Yeah, I don't want
I still have that other what?
the times exp, the thing that you started.
Oh, no.
Oh, I only ran this line.
Yeah.
Okay.
So I fixed it in the homework, but maybe you guys were looking at the earlier version of it. If you change it to the sine, the phases work out right. If you change it, if you use cosine, you get this nasty thing. So you probably notice that it still sounds like a square wave,
That's, yeah, I got that.
but it doesn't look like one.
Funky way.
That's if you take all the phases and shift them 90 degrees. So what we're going to do now is just add a random phase component. Does everyone see how this line is giving us not just the amplitude, but a phase shift? And that phase shift is random. And by making it random, that is my way of telling you that I don't care what it is.
That's gonna be random 0 to 1, right?
Random 0 to 1, probably. What's the concern?
Like 1 and 5 is definitely a dimension, and then it should be 7 because you put 2 more numbers there.
Ah! Yeah, I was looking at the old thing.
And you don't want your phase to be 0 to 1 radians.
From 0 to 1, so you're right in that this won't give you a uniform distribution of,
Well, it's a uniform distribution, but just from 0 to 1.
but not over the whole range. So if we would rather do 2 pi, that's okay. It's not it wasn't uniform across the circle, but it was
So
uniform in its
those
subset of
arguments
the
on
circle.
rand specify how long the vector is, the random vector is, not your.
Yeah.
It's not the range, it's the size. Rand itself gives you numbers between 0 and 1 of floating point type.
Okay.
So 1 to 7 just says between 1 and 7?
No, it says 1 by 7
Give me a 1 by 7.
Gives you a random 1 by 7 vectors.
Matrix
Got it.
of random.
Yeah.
of random numbers that are between 0 and 1. And if you ever have your doubts, help me, Rand!
Oh, Brand.
Uniformly distributed pseudo-random numbers on the open interval 0 to 1. So you'll never get a 0, you never get a 1, but you'll get everything in between if you're patient enough.
Are you still applying the real part?
Yeah, really, I don't care though at this point. So, show of hands. Who understands that this line that's highlighted gives you an amplitude and a phase? The phase is random. Okay. That's enough to keep chugging. So we're going to look at this. That looks just lovely, doesn't it? Just for funsies, we're going to plot a couple of them. For I, let's do something we haven't done yet. M equals 1, 2, 3. And good old MATLAB.
How did you do that? How did you indent?
So to indent, you can do control and then curly brace.
Okay, of course.
You can also hit tab, I believe.
Curly brace is the first letter in
This guy.
You can also. I think tab replaces it with the tab, though. Maybe control tab.
I think it's smart on this one. And you can do tab, no indent. Yep. So I'm plotting it. I'm saying, hold on, don't erase. And then I plot 2 more. So 1 to 3 is going to plot 3 things. Oh, God, it's hideous.
Oh, yeah. It's not the same.
All I expect you to glean from this is that it's not the same. Why don't we do...
It's just so not.
We could, but then I have to set up an array of colors and things. So instead of plotting them, we're going to listen to them and pause. Pauses. sound, 4800 is the frequency. Y is that. Gain 1000, no, we don't want that. Clip all the things. Let's try. We're gonna start this quiet for the sake of our ears. Must be real and floating point.
It's like a while because you do the normalization process and it still complains.
Why don't I hear this? Don't make a fool out of me, MATLAB.
Too late.
Yeah, it would seem so. Well, the exciting thing is that I will put this demo online and you can run this and listen to how the same it sounds every time, even though the phases are different. That's the moral of that story.
Can you try putting 32 at the end of sound?
32 at the end of sound. Why would I do that?
32 bits. I feel like it did that for me once. Like,
Sure, I'll play.
Oh no.
Well,
And only 24-bit audio is supported.
well, I guess I wouldn't expect 32-bit, but
Maybe it is playing.
something is working, but it's not getting all the way there.
It's probably just not on their input or something.
Yeah, just check if you can play any sound.
It is getting to the interface, but it's not going any further than that. And really, I don't know that I want to sit here and debug this right now. I'm just going to leave this as an exercise to the user, which I don't have any.
Square wave.
They all sound like square waves, and this was on the lab, so it should technically be old news by now. That was fun. Let's comment that out. Now we're going to do projections again. I realize we did a very brief coverage of that the other day. I want to do that in a way that is hopefully clearer. So it's going to use some animations. Yay! I'm going to pick an X vector, which is essentially arbitrary, and we're going to project it. Let's start by projecting onto the x-axis. No, let's make this the y-axis since we're already calling it y. And who remembers the formula for projection? X projected onto y is equal to?
The dot product of the two divided by the magnitude of.
So absolute y
That's not all of it.
squared.
Let me bet.
Why is this not all of it? Or who can give a persuasive argument for why this is not all of it?
Oh, that's just the magnitude.
It's just a magnitude, it's just a scalar. So we want something in the direction of a y
Of y, so times y.
times y. Does it work? It's happy. Okay, so now that we have that, let's plot things. You'll see why to hold off there. So in order to plot this, we're not going to just plot the points, but we're going to plot 0 and then the point itself. And the reason is because I want a line that is casted out to that point rather than just the point. So blue line is good. Let's make it thicker. Who would have thought that that would work? So let's see what it looks like. That was strangely unproductive.
What is the argument 3?
What is the argument 3?
The last.
That specifies the line width.
Okay.
Why doesn't it like this? Oh, it doesn't like this because it's not a complex number. We can calculate this quantity using the dot product of y and y. if you don't see why.
I do see a few ones.
That, very good. Love a good pun. Y dot y is equal to, well, let's give this some numbers. So 1, 2, 3 is going to be equal to 1 times 1 plus 2 times 2 plus 3 times 3. And that is equal to, so in order to find the magnitude of a vector, you take each element and you square it, and then you sum them and you take the square root. It's your Pythagorean theorem. So if this was a vector of x, y, and z, it would look like x squared plus y squared plus z squared square root. You lose the square root and you're back to this.
Are we just supposed to memorize the formula for projection, or is there a proof of the y projection? Is that?
Really, it's
Um,
in the video.
Yeah, I'm sure there's a proof in the video. It's not a really hard thing to memorize, I would. So here's a line. It's just a line and it spans a whole screen and I don't want it to. So we're going to do this axis. And this incredibly intuitive command takes the largest and smallest x values and the largest and smallest y values that it should show in one array. So now we have that not doing things correctly. Y. You list the smallest before the largest, of course. It's my first day. Cool. So here is our vector. Now say we also want to plot the other vector. Let's do hold on because we want a second one. We're going to change these to y's. Hot damn, 2 vectors. Let's say we want that to be red. And let's also look at the projection. And in order to make all of these visible, we're going to make the projection a little thinner, make it dotted, and make it green. So you have the blue vector that is projected onto the red vector, and then that result looks like the green vector. You'll notice that the projected vector and the vector that we are projecting it onto are at the same angle. That is essentially the definition of vector projection. It's taking it one vector and casting it down onto another vector such that it's at the same angle as the vector we're projecting onto. And the length is reflective of the length of the original along that component. So this might not be the easiest thing to see here, so we're going to make an animation. So if we pause just a little bit in between each frame and set this up in a loop, oh God. You have to use control and not shift. 4, let's say we want a vector that just rotates around. For I, we can use I, that's the worst thing in the world, is going to go from that to 2 pi, and say we want it to happen in increments of 0.01. And then we're going to end it. Let's see what this looks like. It's very impressive. Why is that not moving?
You didn't put the I anywhere in the function.
Ah,
It is going to give that.
this is why you guys are going to make the big
Oh,
bucks.
that's nice. Look at that.
Okay, so how about instead of using this lovely x vector, we will make something that goes round and round and round. How are we going to do that? We have a variable that's changing.
Yeah.
It's even going
We're gonna
from
need
0 to
sine.
2 pi.
Yeah, we're going to need sine and cosine.
We're going to need some sine and cosine. So let's start it at 1, or I guess 1 from your perspective.
Yeah, so cosine of I and then sine of I.
I suddenly don't like this notation anymore. Let's use theta so that we aren't calling things that sound imaginary. And let's give this a radius. Now hopefully this will be more entertaining. Wow. So do you kind of see what's happening here?
So it gives you like the component of the blue line that's in the red line direction.
Exactly. Very nice. So let's make that go around a few more times, make the delay a little bit shorter.
So when it goes down, it's a negative. You're getting a negative scalar value when it's in the other direction.
But it's still at the same angle. So the red is the y-axis, so it makes sense that the green is always vertical. This is what it means to project something. Say we take, okay. I don't think so. Say we don't want to see that anymore, but say we want to see the x-axis. We should expect a very similar demo. Anyone got any problems with what we're seeing here? And if we want to see the component, right, the component that is getting ignored, we can plot it, or the component that's getting stripped off, rather. That's going to look like x sub 1. It's going to look like this with the x's in there. If you're curious where I came up with this, we can talk about it another time. And we're going to make it k, which is obviously black. That is not what I wanted. That is what I wanted. So that shows the vector component that we're getting rid of.
So it's just like making the vertical part of the vector 0.
Mm-hmm. That's exactly what it's doing in this case, yes. We'll see what it does when I change this so that we're no longer projecting there. It's not quite as simple now, is it? You can see that what this is doing is it's stripping down this blue vector into two components, one of which is along the direction of red, and one which is perpendicular to that. This works in 3 dimensions, this works in n dimensions, this works in whatever. And the black line is equal to, and keep in mind that these are vectors, the blue line minus the green line. So it's the component that is left once you've removed the projection part. So let's do another one. Maybe we make it -2, -3, 4. Why not? And I'll give you guys this MATLAB code. Does this kind of make it clearer what it means to do a projection? This transform is taking the blue line and putting it down onto the green line. Does everyone see that? Is everyone either clear with this or bored with this?
This is projection of blue onto red.
Yes.
And in projection of red onto blue is different?
Mm-hmm. We can do that. So you want to do projection of red onto blue, which is not a hard thing to do. We just have to switch these, and we're still going to have...
Still the dot between x and y. You don't have to switch those.
Yeah. You don't have to switch those for the real case. They're the same. And so now...
Oh, I see.
Well, I mean, our black line is no longer useful.
Yeah, of course. But like that still illustrates that they're different.
To me, this is much harder to look at.
Yeah, it's hard to look at. But it's like clear that they're like they're
Right.
That's different from what we were looking at.
You shouldn't learn a whole lot from what you're seeing right now. The main thing to take away from this is that the green line and the blue line are now always in line. I think that's confusing. We're going to go back to
Yeah, that's fine.
keeping the one that we're projecting onto stationary. So that, oh, stop it, stop it. Okay, so I'm just going to put this up and let this run, and I'm going to talk just a little bit more. Wow, that did not get anywhere near 5 o'clock, did it? Not even close. That's okay. So this shows us what happens when we are projecting one vector onto another. So we're only getting stuff that is in the direction of this. Hopefully this builds a little bit of intuition as to what's happening here with our dot product. We're stripping off every part of this signal that is not similar to S sub k. So everything in X that is not in the direction of S sub k, remember this is in an n-dimensional vector space. I wouldn't think too much about all that. We're finding the components of X that are of this frequency. And it's basically this in higher dimensions, which makes it hard to visualize.
This is as if our signal were only 2 signals long.
I'm not going to make that claim for that this image corresponds exactly to that, because then we would have to figure out what space we're looking at here.
I mean, I'm assuming that we're looking at 2 spaces.
We don't have to. I mean, this is definitely a two-dimensional plane.
But yeah.
I think going down that road is going to confuse people a little bit.
All of the S sub k vectors are all orthogonal to each other, right?
Yes.
So then, if you're gonna have like, you know, n things orthogonal to each other, we need to be in n-dimensional space at least.
Mm-hmm. And we are.
And that's why he wrote n-dimensional space.
Yeah.
Okay, really good.
So words like orthogonal basis might be scary. I'm going to try and make that less scary. Basis means it's kind of like the building blocks that we're using. So when you're in three-dimensional space, the basis that you normally use is your axis that goes to 1, 0, 0, 0, 1, 0, and I guess people like to see it in that direction, 0, 0, 1. And we call these x, y, and z. And you can build any point in this space as a sum of scalings of these. So if you want -4, 3, 0, it should be pretty clear that you take -4 times x plus 3 times y plus 0 times z. And you can construct anything using those. This is your basis. This is your building blocks for a three-dimensional space. When you're building a signal, we are building it out of these sinusoidal components that are all of different frequencies. So when you have a basis of sinusoids and you set bin number, some bin corresponding to 200 hertz equal to 1, and you take 3 times that frequency, 5 times that frequency, 7 times that frequency equal to descending magnitudes like you did in your homework, you're building a square wave. And when you take the FFT axial eraser, if you're looking at something in terms of frequency versus amplitude or magnitude is a bit more exact. You're saying these are the building blocks I used. I used this frequency plus this frequency plus this frequency plus this frequency, each with amplitudes that fall off as 1 over the harmonic number. And you add those together, and what you get is our wiggly little square wave. Every frequency on here is your basis. You're using some vectors from that basis to construct something in the time domain. Thank you.
So K determines like the number of bins, right?
K.
It's how many vectors would be inside your basis vector.
Which K? This K?
Yeah, that K.
This K is any single one of these.
Right.
So here's a K, 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 here's a K. But the number of Ks that you have is big N.
Okay.
So big N tells you how many different bins there are, how many different frequency are, how many different basis vectors there are, how many building blocks for a time domain signal you have.
Okay. And what would determine how, in what dimensional space you are? That means like how big each vector is.
That's also N.
Oh, so it's
So the number of samples that you have in time becomes the number of bins that you have in frequency,
Which is the dimension of the space that you're in.
which is the dimension of the space that you're in.
why is it the dimension of space that you're in?
The number of bins that you have.
Yeah, it's the
dimension
number.
of the Hilbert space or whatever you want, the space that you're in is the number of bins, the number of basis vectors that you have.
Mhm.
And does that mean that each basis vector would have is as long as the number of bins?
Each of those vectors is as long as the number of bins.
Like they have that many elements inside of it?
Yes. And then you take those basis vectors and you scale and shift them using this. So you multiply each basis vector times its corresponding x sub k, which contains not only a magnitude or an amplitude or whatever you want to call it, but also a phase. It's a complex number. And you get the component at that frequency that you'll need to sum with the other components of different frequencies to get your square wave, to get your sine wave, to get your Beethoven sixth. Is that clear? And I mean, if you have Beethoven sixth, you don't have two samples. You have hundreds and thousands of samples. So when you look at that in frequency, it's not going to be neat. It's not going to be fun like this. It's going to be a mess. But when you take those frequencies and you add them back up and you convert it to time domain by, that's what you're doing when you convert it to time domain, you're going to get that signal back. Questions on that? It's not necessarily simple stuff. Hundreds of years of theory went into this. Questions? Julius, are you still there? Okay, bye.
One question about,
Thank you.
I don't know if it's just a terminology thing, but I guess with Azim, I'm not sure what dimension is standing for in this case.
It's the number of basis vectors you have.
Okay.
So this is three-dimensional because it only takes three basis vectors to represent the entire space. If you're just talking about the board, you can get any point on this board using an up and an across arrow with some scaling. So your board is how many dimensions? 2. Your free space is 3. If you want a signal with n points, each of them, you can think of this as something that n arrows that go off in directions you can't visualize. I don't think that's going to be helpful for anyone, though.
That's where straight.
But exactly what you have is, if you think of it as not just, 3 numbers, but n numbers, that's essentially what you have. You have your signal vector. So you have an n-dimensional space that is your signal, and you can represent any signal using a summation of sinusoids at frequencies 0 through n.
I think if you just break it down into just having 3 and showing how you can make a linear combination, then that would be helpful to understand.
Okay.
We did, but just to do it again, because I think that would answer the question. Like the 0, 1, 0, 0, 0, 1, and 1, 0, 0. How that's a linear combination. How you can make anything.
Are you talking about 3D space, or are you talking about kind of the thing we did on Tuesday where I had the J's up there?
The 3D space.
Okay, good, because that's easy to explain. Once you start throwing the J's in there, it gets really hard to visualize. These are spaces you can't visualize. If you're trying, you're wasting your time. You're going to lose your mind. If you've already lost your mind, don't let me stop you. Three-dimensional space. You've got your three basis vectors. Again, what's this one? 1, 0, 0, or x.
X hat.
Sure, we can call it x hat. Who was that? Is that you? Physics.
Well, it's normalized to 1.
It is normalized to 1. I'm not saying you're not correct. Don't take away my right to yell at you. 0, 0, 1 is your z hat, and 0, 1, 0 is your y hat. These are your basis vectors. If you want to construct a point that's here, and we can give these some numbers, what's a reasonable thing? Let's say that this is 0 on z, and it's 3 by 2 on the y. Drawing is not to scale. We can take, this is the part where, Ross, you already know this stuff. Find me a new colored marker. This is putting people to work. We can take 3 of those plus 2 of those. Thank you very much, sir. We'll give these all different colors to get that. If we want this space, so this point that's down over here, say, let's call it -3, 3, 2. Watch Chet fail to make this work out quite right. We're going to go out a distance of, oh, come on, of 2. This is really not to scale. Oh, shorter was better. And then we're going to go -3 in x. And then we're going to go 3 in y. So this is just basic three-dimensional space stuff. This should be clear. I'm hoping this is clear. When you take that to n-dimensional spaces, you're essentially doing the same thing. Each of these components then represents a sinusoid, which makes it really tough to draw. But we can see from the simple case over here, why don't we, since we've got extra time, I assume you're still hanging out because you want to see this thing. If you've already got it, you might be bored, in which case you don't have to stay, but I enjoy your company. Sound really lonely. Let's talk about this 2-point example again. So you've got 2 points, say here and here. And we're trying to construct this using a sum of scalings of these, just as we tried to reconstruct this using a sum of scaling of those. So without going too much into the math, let's make this green. We know that we're going to have the contribution from k equals 0 that looks like this. So this is equal to that, where this height here goes right through those. So we know there's something else here. How do we get what that something else is? We can subtract this off. And then all we're going to be left with is that. Where these two green lines here are going to be equal to the length of the green lines from this. So we're going to have the down and the up. These are equal in magnitude, opposite in direction. These are equal in magnitude and direction. And you can sum them up to get this signal here. This requires scaling, of course. You're going to scale this guy here to whatever height this becomes, whatever the average of these points is. And you're going to not just scale this, but you're going to flip it. You're going to scale it by a negative number to get these differentials back.
And what are those scale factors?
You want to bust out some numbers?
Sure, if you want. But I mean, if you just want to understand.
Why don't we
Tie it back into the
why don't we say sure no, why not and bust out some numbers?
But what are we doing right now? Is this projection?
So this is the green component on that thing that rotates around and round. This was what we're projecting onto. This is what we're the orange is what we're projecting from.
He's doing a DFT that involves projections onto those bases.
Yes. So this is a DFT. It's also those projections. I heard a question in the making, maybe.
Since it's a 2-point, he's got a 2-point, signal.
Yeah.
And so he's got two basis factors. And so he's doing the DFT by projecting onto those two basis factors.
And those two basis vectors are the black ones?
The black and the green.
Yes. These
Black and the green.
Black and the green.
these are your basis factors.
One with frequency 0 and DC average component, and frequency of pi.
You can see how we can make any signal, any two-sample signal out of those two things.
And
Do we want to give this some numbers and do a little math? We can.
I think you can like visually.
I think you can too.
But, I don't know, maybe math.
But if I'm not reaching someone that I can be reaching, I want to.
yeah, all I was saying too, though, was that those amplitudes of the two basis factors are the x and k's.
Yes.
That's all I was. You
Yes.
don't have to do the numbers, but.
No. And really there's no need for numbers.
X.
Which
Ju-
amplitudes?
The magnitudes of the decomposition of that, red signal onto the basis of black and green, the black amplitude is x0 and the green amplitude is x1.
X1 is going to be negative.
And in this case, they're both real.
They're both real. Yeah, complex numbers don't even enter into this example because the two frequencies we're looking at are 0 and pi, which are both on the real axis. So
As soon as you bump it up to like 3.
as soon as you bump it to 3 or 4, anything above 2, there's complex numbers and it gets hard to visualize. My goal is that you guys can visualize this in the simplest cases, and to some degree you trust that it applies. You can prove that it applies, of course, but it's going to be more intensive. So is this clear? Can I see a show of hands for people who understand this? Lovely. Any following questions? We've got 17 minutes or less if you want less, whatever you like, for you to either grill me with questions or go get cheeseburgers or whatever kids do. I don't know. Texting and scones.
We have
I haven't heard that joke in a long
xk
time.
dot product, xk with sk dot product equals large xk.
XK,
The dot
XK.
product of xk and sk equals.
Oh. This guy.
You said that's doing the projection we're doing here, but when we do projection, we divide it by the magnitude of the projection vector. Do we not?
You do. The magnitude of these is 1.
How's that?
Yeah.
They're
Be-
with all
They're an orthonormal basis for those who know what that means. Essentially what it means for those who don't is that this just comes up to the number 1. Dividing by the number 1 is trivial. So this is your, in the projection formula, this is your x comma y, your inner product of x and y, your your y comma y, in this case, is equal to 1. So orthogonal basis means you have this basis, this building block for your space, where each component is 90 degrees from all others. Orthonormal is a fancy word that means they're all of length 1. Did I lose anyone? It is your job to yell at me if I've lost you.
Is it also true that that in an orthogonal basis, the dot product of any two vectors is 0?
Yes.
Yes. The dot product of any two basis vectors.
Yes.
Yes. Any two orthonormal things, if you dot them together, you get that it's 0.
Unless you're dotting it with itself, in which case it's 1. That's orthonormality. Orthogonality.
Yes, but dotting it with itself is not dotting two orthogonal things. It's dotting two things that are in the same direction.
Oh, I must have missed it.
It tends to make some long sentences. Other questions? Got about 5 more seconds for raising your hand and saying, I have a question before I ask a question at you. Okay. Was what happened today useful to you? Send me your slings and arrows. Was this better than how it has been?
Yes.
Assume Julius is here and I'm stopping him just as often. I don't like the Skype thing any more than anyone else does, but when he's in Denver, that's what we have to do. Can I get a show of hands for people who do like this better than the random crap? I'm hoping to see a lot. Okay.
You said it well, like shutting down the fire hose for a second and explaining what the commands are.
The fire hose needs shut down every once in a while, yes. Okay, I saw all the hands. If there are people that didn't want to, keep their hands down or that don't like it, please talk to me.
You can anonymously put your hand down on Piazza.
Or do that. Whatever gets your feedback to me. I don't want people to suffer through this for the entire quarter, because if you haven't seen it, I acknowledge that it is hard, and I'm doing my best to help you out, but you got to help me help you out. So yell at me, yell at Julius, yell at everyone. Help me put the brakes on the fire hose.
I think the key is, well,
Also, if you're bored, talk to me. I'll give you hard stuff. But that's just beside the point.
when you explain, you make sure you haven't lost anybody, and that's just completely not a part of Julius's game plan.
I'm working with him.
It's
I'm working with him.
You have to speak up if you have any questions, but if you're lost, you can't ask a question.
Yes,
You
I
never
know.
ask a question if you're lost.
That's what I'm trying to
Like,
combat.
okay, well, class, can you just go back and explain all that again? Because I didn't get any of it.
Mhm.
But yeah, and also consistently relating it back to things that make sense in real life, as opposed to just on the white paper.
Agreed.
Just huge.
Yeah, the visuals were super helpful. Just seeing that representation of how the basis vectors, add together to create the original system.
Very good. Okay, so some administrative notes, and then I'll let you go. If you haven't turned in homework 1, turn in homework 1 to me today, because I'll be releasing the answer key. If you haven't turned in homework 2, turn it into me as soon as possible, because I'll be releasing the answer key. If you have some circumstance that makes you a different case, then talk to me, or you should have talked to me already. That's fine. But if you're not some special case, turn the homework into me so that I can release the solutions to people who want them.
Homework 3 is Tuesday.
Homework 3 is due Tuesday. Homework 3, the lab, is due on Friday. That will be released, I believe, by the end of today. There's another question with additive stuff. So between what I showed you today and what you did for lab 2, that should be a pretty piece of cake. And then there's one that starts with Fourier transform stuff, which means you're calling it, not you're necessarily computing it the hard way. And we will talk about that more on Tuesday. You're giving me a look. Is this an okay look? Oh, good. Okay, you're free.
What do you mean by calling it?
There's an FFT function.
Oh, okay.
You'd rather call that than write it. Yeah, we talked about it briefly.
So I'm just gonna stop.
Yeah, that's fine. Now, in terms of like progress and where you want to, let me take care of this. This will take 2 seconds.